Now this video has shown the calculation of bending capacity of double reinforced beam and also introduce the double reinforced beam. So let's talk about doubly reinforced beam. Reinforcement compression zone is present in the beam. So as in the previous video explained, in doubly reinforced beam we have an additional reinforcement in the compression zone. The purpose of this reinforcement and compression to hold the fitment stirrups in the place. So if I draw these doubly reinforced sections, we have a stirrups. So that stirrups can be held properly if you provide the compression reinforcement. This is compression reinforcement in the place and improve their anchorage. Increase the MUO if the beam size B and D is restricted. So if the architecture don't allow to increase these dimensions, this additional reinforcement increase the bending capacity, and it also improve the ductility and also reduce the long-term deflections. Now this is a typical case for the beam sections. We have tensile reinforcement, we have compression reinforcement in the doubly reinforced beam. Depth D, small b, this is the neutral axis which is represented by dn. Small d is the distance from top fiber to the center of this reinforcement. We have a maximum compression strain 0.03. This is the compression strain in the top reinforcement. This is a tensile strain in the bottom reinforcement. So it's a strain distribution, three different strain: concrete strain, top reinforcement strain, and bottom reinforcement strain. Then stress distribution, respectively we have three forces. Compression force in the concrete, alpha to fc dash. This is the equivalent stress, so the depth is gamma dn. And we have a compression force in the top reinforcement, which is represented by sigma sc, and we have tensile stress in the bottom reinforcement. Correspondingly we have three forces. That stress in the steel has a similar times by area of the top reinforcement give us the compression force in the steel, and we have a compression force in concrete. And please note this distance is the distance from center to the top fibers, and we have this centroidal distance for this half gamma dn, and we have this tensile force for this bottom reinforcement, and we can calculate MOU by taking the moment that we discuss later. Now for the given cross section and reinforcement, MUO can be determining using the trial depth of the neutral axis and corresponding strain distribution diagram analysis. If we don't know this dn value, we need to assume the dn value, and we need to try and we can find the MUO. At the first trial, assume ASC is yielding, so we should know that we make the assumption that the top reinforcement at yield. These assumptions need to be checked for the trial dn value, and note that AST will be yielded, and hence sigma tensile steel force is equal to yield stress. Now there are, as I mentioned, there are three forces that we are dealing with. First one is the compression force in the top reinforcement, so that is the area of the top reinforcement times the yield strength. Second, we have a compression force in the concrete above the neutral axis, that has a stress alpha to fc times the area b times gamma dn. And we have a tension force in the bottom reinforcement. This is again stress times area, ast times fsy. Now for the horizontal horizontal equilibrium, we can have cs plus cc minus t, so that is should be equal. So if you substitute this value, cc is alpha to fc b gamma dn, plus we put cs value, compression force in the top reinforcement. This is this equations, and we substitute this here, and if you simplify this, we can find dn value of dn equations for this for using this equation 1. Now for this dn equation we need to do some check now the strain ESC in the compression strain. Using the similar triangle in the strain distribution, ESC can be found. So if you come back here, ESC divided by dn, and this is DSC. So this distance dn minus DSC. So you can see ESC. So this small triangle is here, ESC, and this one would be dn minus DSC. And similarly we have another triangle which is big one here, which would be big triangle here, which would be 0.03 and dn. So 0.03 dn. So based on these equations we can calculate ESC. Then we can compare with ESY. ESY is generally 0.0025. If ESC value is greater than ESC, then the assumption that the compression steel is yielding is correct, and the value of dn calculated using equation 1 is therefore correct. The moment capacity MUO can be calculated using the equation number 3 that is on the next page. So if this condition is okay, then we can calculate the moment. But in case if this strain in the stop reinforcement is less than the yield strength of the steel, then the neutral axis depth from equation 1 is not correct, and we need to use the iterative process. Now this iterative process we will take the examples how to. So we need to select the new trial value of dn. Generally whatever we calculated from the equation 1, we need to take the larger than this dn value. We need to take a larger than equation 1, and using equation 2 we need to calculate ESC. Using equation number 2 we can calculate ESC. Once we calculate ESC, we can calculate the sigma stresses on the reinforcement, top reinforcement, compression stresses by multiplying the Young modulus with ESC that we calculated, and we can calculate the force CS, which is the top reinforcement force. If I take the this one, so this force is the compression force in the top reinforcement, area times stresses that we calculated here, and we recalculate the compression force in the concrete using this one, because we have new dn value here. So we can use these equations to calculate CC, and we check whether for this new dn we have this equilibrium is satisfied or not. If this is true, then we need to check whether the ductility condition is satisfied, Ku is less than 0.36, and then compute the moment capacity from the equation number 3. This is just nothing but it's just T times D. This whole thing is D. So T times D, CS times DC. So this CC times this DC, and CS times DSC. So we also need to check we also need to check the minimum fluxure capacity. That should have a P greater than P minimum, and P should be less than P maximum for ductility. Thank you very much.